Hello everyone, welcome to Pre-Lecture 12. This is going to cover some more ideas around the Chatlier's principle. So last class we defined what Le Chatelier's principle is and what it applies to. Essentially, if we have a system at equilibrium and it experiences a stress, that can be the addition of more reactants or more products or possibly a change in pressure or temperature, then Le Chatelier's principle states that the reaction will move, so form more products or form more reactants in order to reestablish equilibrium. Okay. And an example we went through, or two ways we interpreted one example, were with H2 and I2. So we can have a kinetic interpretation of if we increase reactants in the reaction, then the rate of our forward reaction will go faster, meaning that the reaction will ultimately shift to the right and we'll end up forming more HI in total. The reverse being true as well, that if we were to add more HI to our reaction mixture, then the reaction would reverse reaction, would speed up, and that would ultimately form more H2 and I2. Okay, so that's our kinetic interpretation of Le Chatelier's principle. We can also think about this in terms of a reaction quotient. So if we just do our products over reactants raised to the powers, then we would have HI over H2 times I2. And if we think about basically as our denominator grows larger, that means that Q will get smaller. And so if we add more reactants, denominator gets bigger, Q gets smaller, and in order to reestablish equilibrium, we have to move our reaction to the right. And so hopefully that all rings a bell. Obviously, you can read through these slides again. If you have any questions, please let me know, because this will be important for us to get through the rest of class. And so in this pre-lecture, I'm going to introduce how Le Chatelier's principle will change based on changes in pressure and temperature. And so if we start with pressure here, rather, a reminder that if we rearrange our PV equals nRT equation from Gen Chem 1, then a change in our volume or our pressure can result in a change in our equilibrium position. Okay. And so an example we can use for that is this reaction where we have 2NO2, which we generated in lab this week, and that can decompose to, oh no, wait, sorry, that was Gen Chem 1, sorry, different lab. But we have 2NO2, and that can decompose to 2NO and O2. And so if we were to write the K expression for this, it's products over reactants raised to their powers, it looks like that. And say, for example, if the volume of our container, because all of these are gases, if the volume of our container were to become 3 times smaller, then that would mean that the partial pressure of all of our species is going to triple. And so we could put a 3 in front of all of our partial pressures, because when we decrease our volume by 3, we're going to increase the pressure by 3 times as well, if you look at the relationship between pressure and volume there. If we then distribute our exponents, so you'll notice that the partial pressures for NO and NO2 have a squared exponent. So if we distribute that, that becomes 9 for each of those terms. And then if we combine our terms, we end up with 27 over 9. And if we simplify that, then in order to calculate Q, we would figure out that 27 over 9 would be equal to 3 times, Q would be 3 times of K in this sort of situation. And so that's just how we can think about how changes in pressure and volume relate to changes in Q versus what we start with, with K. Sorry, before I go on to talking about temperature, if Q is going to be greater than K, that means, of course, that we have to shift our reaction back to our reactants in order to reestablish equilibrium. And so as a general rule, you can look at a reaction and figure out which side of the reaction has more moles of gas. So we have 2 moles of gas on our reactant side because we have a 2 in front of NO2. Then we have a 2NO and 1O2. So we have 3 moles of gas on our product side. And if we increase our pressure, then that means we will shift to the side with less moles of gas. And then of course the opposite being true of if we were to increase our volume or decrease our pressure, we would end up forming more of our products, our NO and O2, because Q would then be less than K, so our reaction would shift to the right. Okay. All right. So talked about pressure, we can also talk about temperature, and K, our equilibrium constant, is something that is temperature dependent. This ultimately relates back to the Arrhenius equation that we talked about, but you don't have to think all the way back there. I'll give you some shortcuts to think about that in terms of equilibrium. And so with equilibrium, we are generally concerned with if a reaction is exothermic or endothermic. And so we think of things in terms of enthalpy. So for a separate reaction where we have N2O4 that can decompose to 2 moles of NO2, if we have an enthalpy of 57.2 kilojoules per mole, that means this is an endothermic process, right? Because we have a positive delta H value. Because it's endothermic, we can actually consider heat to be a reactant. And so if we do that, if we raise the temperature of the reaction, that is like adding more reactant, which ultimately means we would shift towards forming more products, right? So we would move our reaction to the right. And then, of course, the opposite would be true. If our temperature went down, then we would form more reactants, okay? The opposite will also be true if the reaction is exothermic, where heat would then be a product instead of a reactant, okay? Another thing to think about that hopefully you remember from last unit, but the effect of a catalyst on equilibrium. So if we have a one-step reaction here and our red represents our uncatalyzed reaction, our blue would be our catalyzed reaction. All the catalyst does is lower the activation energy, right? And so we have a lower activation energy, which is going to speed up our forward reaction, but it's also going to speed up our reverse reaction, okay? So because of that, a catalyst will not actually change K. It will only help us to establish equilibrium faster. There will be no change in the ratio of our products over our reactants, okay? Hopefully that makes sense based on what you know from last chapter even. One reason this might be important is something called the Haber-Bosch process. So just to kind of tie in an application here, this is what a Haber-Bosch reactor looks like. And so it was first invented in 1918, and it's actually the most used catalyst in the world, and 1% of the global energy every year goes to this process. And what it does is ultimately produce ammonia that's used to produce fertilizer and ultimately feed about half the world's population. And so not only half the population, but probably about half of the nitrogen atoms in your body originated from the Haber-Bosch process being used to fertilize something. So just to give you an idea of how important it is. And really without this, if you'll see prior to 1918, we had a pretty flat growth curve. And then all of a sudden our growth curve takes off once we introduce synthetic fertilizer. And really all of the population growth that we've had in the last 100 years or so is due to the use of synthetic fertilizer that we're able to produce with this catalyst, okay? And so why am I bringing this up in our equilibrium unit? It's because the reaction involved in the Haber-Bosch process, where we start with N2 and H2 gas and ultimately produce ammonia, has a small K value. So its K value is about 1 × 10⁻⁵, meaning that our reactants are highly favored. But if we do this at higher pressures, high temperatures, and with a catalyst, and importantly, maybe most importantly, with Le Chatelier's principle, we have a condenser that removes ammonia from our reaction vessel that will actually allow us to continually produce ammonia in a fairly effective manner. And so that means that we can actually, again, feed the whole world using this Haber-Bosch process. And another interesting side note with this, one of the scientists who helped develop this was Fritz Haber. So he won a Nobel Prize for this work, at least half of a Nobel Prize in 1918. However, soon after that, he was German, and he is actually considered the father of chemical warfare because he invented most of like mustard gas and basically all of the chemical gases used during World War I. And so he has this very mixed reputation of being someone who fed half the world, but also invented chemical warfare, which is not really something that you want to be known for, maybe, and something that people look nicely upon. So anyway, just an interesting tidbit for you there. Hope that was informative and you learned a lot. I will see you in class soon, and I hope you have a good rest of the day.